Hello and welcome back. We are coming at you with incredibly high energy today because we are tackling something that is uh, literally the foundation of everything.
I see what you did there.
I mean that in the most literal sense possible. We are talking about the ground beneath your feet. This is the full summary for UPSC, focused by Simplified UPSC by PPP YouTube channel.
It is, and if you're listening to this, you're not just here to pass time, are you?
Not at all. You are here to build a fortress of knowledge, specifically for general studies, and we are, the architects helping you lay that foundation.
It is fantastic to be here, and you're absolutely right. We are building the scaffolding today.
Mm.
But before we pour the concrete and get into the geology, we have some very important community business to attend to.
We do. The really important stuff.
We really want to humbly ask you, the listener, to subscribe to the channel. I know everyone says it, but it sounds like such a small thing, just clicking that button.
But it makes a massive difference.
A huge difference in our ability to keep these deep dives coming your way.
It's absolutely the fuel for our engine. And look, let's be real for a second. If you are capable, and I want to stress this, only if you are financially capable, please consider supporting the team on Patreon.
Mm-hmm.
It ensures we can keep bringing this super useful content to you without interruption. And on that note, we have to give a massive, warm shout out to all our current supporters.
A huge thank you.
You guys are the bedrock pun fully intended of this entire operation. We literally couldn't do it without you.
We really couldn't. Also, a quick one. Don't forget to engage with the algorithm.
Ah, the algorithm.
In the audio world, that means liking this video and sharing your valuable comments.
Yeah.
We actually read them.
We do. They aren't just shouting into the void. They help us shape future discussions and, understand what you need from us.
Exactly.
Okay, one last resource alert before we start digging deep.
The good stuff.
There are free notes with practice previous year questions or PYQs available right now on the public Telegram channel.
Yeah.
But if you want the VIP treatment,
And this is the game changer.
it really is. I'm talking access to all videos in this series at once. Organized premium notes that are beautifully structured, extra PYQs, and model mains answers.
You need to DM on the public Telegram channel to join the private Telegram library. It is a total game changer for your preparation.
It really is.
Okay, housekeeping is complete. Shall we switch gears and turn on the drill?
Let's do it. Transitioning into our deep dive persona, today's mission is to crack open the Earth. Literally, we are covering NCERT Class 7 Geography, Chapter 2, Inside Our Earth.
And I can already hear it.
I know what some of you are thinking. I can hear the skepticism through the headphones.
Right.
Class 7. Seriously. I'm preparing for the civil services, the toughest exam in the country. Why are we reading a book written for 12-year-olds?
It is a fair question. It really is. But let me tell you, it's also a trap.
A trap. How so?
A massive trap. The biggest mistake aspirants make is assuming they are too advanced for the basics. They want to jump straight to complex geopolitical theories or, advanced geomorphology without understanding the vocabulary.
You can't run before you can walk.
You can't. This chapter, Inside Our Earth, it forms the bedrock of physical geography. If you don't understand the crust, the mantle, and the rock cycle here, in this simple text, you are going to struggle, and I mean really struggle, when you hit advanced tectonic theories or resource distribution questions in the mains.
That's a great point. You can't write a Shakespearean sonnet if you don't know the alphabet. So the roadmap for today is pretty exciting. We are going to explore the 3 layers of the Earth, get into the chemistry of the crust. We're talking Sial and Sima.
Tectonics, yeah.
Break down the 3 types of rocks, spin through the rock cycle, and finally, and this is the best part, we are going to link this foundational knowledge to actual high-level UPSC Mains questions from 2014, 2016, and even the 2025 paper.
That is the goal. We take the simple text and show you the complex application. We're going to show you how a simple sentence in a 7th grade book becomes, a 15-mark answer in the exam hall.
All right, let's start with the very first image the NCERT gives us. It's an image everyone knows. The text says, just like an onion, the Earth is made up of several concentric layers with one inside another.
The onion.
An onion. It's a classic analogy. Shrek used it, and now the NCERTer is using it.
It's classic because it works visually.
Right.
It really does. It helps you visualize that idea of layers peeling back one after another.
Right.
But while it works for structure, I think it fails on scale. The sheer magnitude of it all. We need to understand that. We live on the surface, the very thin skin of the onion,
Just the papery bit on the outside.
Exactly. But have you ever thought about how little of the Earth we have actually seen or, touched?
Well, we dig mines, right? We've been digging for resources for centuries. The text mentions the deepest mine in the world is in South Africa.
It is. It is about 4 kilometers deep,
Yeah.
and that's primarily for gold. Humans will do a lot for gold.
4 kilometers? That sounds like a lot.
It does. In the search for oil, engineers have managed to drill a hole about 6 kilometers deep. That's the record, I believe.
6 kilometers. Okay, 6 kilometers sounds pretty deep. If you had to walk 6 kilometers, it would take you over an hour. It feels like a significant distance.
It feels significant to us because we are small. We live on a human scale.
Yeah.
But you have to realize the size of the planet to reach the center of the Earth, which is scientifically impossible for us right now.
Not just hard, but impossible.
Completely impossible. You would need to dig a hole 6,000 kilometers deep, and that is starting from the ocean floor, which is already lower than the land.
6,000 kilometers. So we've scratched 6 kilometers out of 6,000. That is, let me do the math, that's 0.1%.
Exactly. 1/10 of 1%. It puts human achievement in perspective, doesn't it? We are incredibly proud of our drilling technology, but we haven't even broken the skin.
Wow.
The text is very clear on this. It says, to reach to the center of the Earth, which is not possible. It uses that exclamation mark. It wants the student to understand the sheer impossibility of the task.
So why is it impossible? The book mentions high temperature and pressure in the core, but it doesn't really dwell on it. Is it just that our drill bits would melt?
It's much more than that. It's a thermodynamic barrier. As you go deeper, the geothermal gradient kicks in.
But what?
Geothermal gradient. It just means it gets hotter the deeper you go. For every kilometer you go down, the temperature rises by about 25 to 30 degrees Celsius.
So by 6 kilometers, it's already pretty hot.
It is, but by the time you reach the core, you're looking at temperatures comparable to the surface of the sun. We're talking thousands of degrees Celsius, 5,000, maybe 6,000 degrees.
The surface of the sun. Okay, no drill bit is surviving that.
Nothing. It would vaporize. And that's just the heat. Then there's the pressure. It's the weight of the entire world pressing down on you. Millions of times the atmospheric pressure at the surface. It would crush any equipment we currently possess like a soda can.
So when the book describes the interior, the mantle, the core, it's really important to remember that this model is inferred. We haven't been there. We haven't seen it.
Correct. It's a model built on indirect evidence. It's a really good model, but it's not based on direct observation.
How do we get that evidence then?
We use seismology. When an earthquake happens, it sends waves through the earth. These are called seismic waves. There are P waves and S waves.
Right.
And these waves bend and reflect depending on the density and the state of the material they pass through. S waves, for example, can't travel through liquid. So when we see that S wave stop at a certain depth,
We know there's a liquid layer there, the outer core.
precisely, it's like a doctor using an ultrasound. We can't see the baby directly, but we know it's there by the echoes. The waves tell us the story.
That's how we know the radius of the Earth is 6,371 kilometers. Not by measuring it with a giant tape measure.
Exactly. We are just scratching the paint on the surface. We've figured out the size of the sphere by listening to its echoes.
So let's talk about that paint, that thin layer on the outside. The crust.
The skin of the Earth. The NCERT defines it as the uppermost layer over the Earth's surface. And the key thing to remember is that it is the thinnest of all the layers.
Thinness is relative, though. The text distinguishes between the continental masses and the ocean floors. And this is where the details get really interesting for an exam like UPSC.
Yes, this isn't just one uniform shell. It's not like an eggshell. It has different properties in different places.
So on the continental masses, the land we live on, the mountains we climb it, is about 35 kilometers thick.
Right. 35 kilometers on average. It can be thicker under big mountain ranges like the Himalayas.
But on the ocean floors, it is only 5 kilometers thick. That's a huge difference.
It is 7 times thinner.
This is where we get our first set of mnemonics, which I love. Mnemonics are lifesavers in these exams.
Absolutely. They help you lock in the facts.
Let's break down the chemical makeup. For the continents, the text says it is silica and alumina. So Sial.
Sial.
Right, Sial. Think of it as Sial, silica and alumina. This represents the upper crust, the granitic rocks. It's relatively lighter. And for the ocean floor, the text says silica and magnesium. So Sima.
Sima.
Sima, S-I-M-A. Silica and magnesium. This is the basaltic rock of the ocean floors.
Okay, so here's the question that immediately pops into my head. The oceanic crust is way thinner, only 5 kilometers, but the continental crust is 35 kilometers thick. Why does the thinner one sit lower? Why are the oceans deep and the continents high? Shouldn't the thicker one be heavier and sink?
That's a fantastic question. It's counterintuitive, isn't it?
No.
But it's all about density, not just thickness.
So it's not about the size, it's about the The weight per unit volume.
Precisely. Sima contains magnesium. Magnesium is a heavier, denser element than aluminum, which is the main component of Sial.
Ah, so the oceanic crust is made of heavier stuff.
Much heavier stuff. It's denser rock. And because it's heavier, it sinks lower into the semi-fluid mantle beneath it. The continental crust, the Sial, is like a fluffy iceberg. It's thick, but it's less dense, so it floats higher.
That makes so much sense. So the water just fills in the low spots, the depressions created by the heavy Sima rock. Exactly. It's the principle of isostasy, though the 7th grade text won't use that word yet. But for our listeners, that's the concept you need to understand for higher level answers. The lighter continents float high, the denser ocean floors sit low.
The text also drops a mind-blowing statistic about volume. I had to read it twice. It says the crust forms only 1% of the volume of the Earth.
1%, just one. Imagine that.
It's hard to even picture.
Everything we know, every mountain, every ocean, every city, every mine, every historical event, every dinosaur fossil we've ever found is in that 1%.
The other 99% is just this massive hot engine beneath our feet that we've never seen.
It's incredibly humbling, isn't it?
It is. Okay, let's go deeper then. Let's talk about that 99%. Beneath the crust is the mantle.
The mantle. This is the big one. It extends up to a depth of 2,900 kilometers below the crust. If the crust is the skin of the onion, the mantle is all the fleshy layers inside. It makes up 84% of the Earth's volume.
84%. So this is the bulk of the planet. If the Earth was an egg, this is the white.
It is. And while Chapter 2 describes it simply as the layer beneath the crust, Chapter 3, which is the next chapter of the book, hints at its behavior. And we need to bring that context in now.
Right, because it's not just a solid block.
Not at all. This isn't just solid rock sitting there. This is where the molten magma moves. The upper part of the mantle, a layer called the asthenosphere, is plastic. It's not quite liquid, not quite solid. It flows like very, very thick honey or tar.
And this is the engine room.
This is the engine room of the Earth. The rock cycle, which we will discuss later, relies on the mantle to melt rocks back down. Plate tectonics, which causes earthquakes and volcanoes, is driven by the movement in the mantle. Without the mantle moving, the surface would be geologically dead. No mountains, no continents drifting.
And then finally we hit the center, the core.
The innermost layer. It has a radius of about 3,500 kilometers. It makes up the remaining 15% of the Earth's volume.
And the mnemonic here, we had Sial and Sima. What's the core?
The mnemonic here is Nife, N-I-F-E, stands for Nife, nickel and ferrosus.
Ferrous, meaning iron.
Ferrous, meaning iron, from the Latin ferrum. So the core is a giant ball of nickel and iron. The text says the central core has very high temperature and pressure, extremely high. And that ferrous part is crucial, iron. Since we are doing a deep dive, let's connect this to the bigger picture. We have a spinning ball of conductive metal, mostly iron, at the center of the Earth. What does that give us?
A dynamo. Magnetism.
Precisely. The Earth's magnetic field. The text doesn't explicitly say magnetic field, but by identifying the core as Nife, it gives you the chemical reason for why our compasses point north.
Oh.
The movement of the liquid outer core, which is made of this iron and nickel, generates a massive electrical current, which in turn creates the magnetic field.
So without that knife core,
we wouldn't have a magnetosphere. We wouldn't be protected from solar winds and cosmic radiation. Life as we know it likely wouldn't exist on the surface. So the chemistry of the core dictates the habitability of the planet.
I love that. It connects chemistry, physics, and geography all in one concept. So we have the crust, Sial and Sima, the mantle, the bulk, and the core, Nife. Now let's look at what the crust is actually made of on a more tangible level, rocks and minerals.
Right, the building blocks. The definition the insert gives is simple but very broad. Any natural mass of mineral matter that makes up the Earth's crust is called a rock.
Any natural mass, so it's not just the hard stuff we think of. And they can be anything, hard, soft, different colors. The text says rocks can be of different colors, size, and texture.
That covers everything from a soft clay you can mold in your hands to a hard diamond. They're all technically rocks in the geological sense.
And we categorize them into three major types, the big three.
Igneous, sedimentary, and metamorphic. And understanding these three is fundamental to everything else in physical geography.
Okay, let's break them down, starting with igneous. I love the etymology here. The text says it comes from the Latin word ignis, meaning fire.
Fire rocks. It is a perfect name. These are formed when molten magma cools and becomes solid. That's it. It's the simplest definition.
And because they are the first to form from the magma, the text calls them primary rocks.
Primary rocks, meaning all other rocks ultimately come from these, right? In a way, they are the parent rocks of the planet.
So in the cycle, everything starts as magma. Every atom in a sedimentary or metamorphic rock was, at some point in deep time, part of an igneous rock.
That's a great way to think about it. It all originates from that molten state.
Now, the text splits igneous rocks into two subtypes, intrusive and extrusive. And it uses a really vivid description here. It asks, can you imagine lava coming out from the volcanoes?
Fiery red molten magma, the test calls it. It's trying to paint a picture of destruction and creation happening at the same time.
So extrusive rocks. Extrusive sounds like exit.
That is a good way to remember it. Lava exits the volcano, it comes out onto the surface. Now think about the environment on the surface. Compared to the mantle where it came from, the surface is freezing.
Relatively speaking, yeah.
So when the lava hits the air or the ocean water, what happens to its temperature?
It drops instantly, it flash cools. The text says it rapidly cools down and becomes solid.
Rapid cooling. That is the key mechanism. Listeners, if you take one thing away about rocks, let it be this. Crystal size is determined by cooling speed.
Okay, say more about that.
When something cools rapidly, the atoms and molecules don't have time to travel and arrange themselves into nice, neat, large crystal patterns. They get locked in place almost instantly. So extrusive igneous rocks have a very fine-grained structure. You can't see the individual crystals with your naked eye.
And the example given.
Basalt. And the real-world application provided in the text is the Deccan Plateau. The entire Deccan Plateau is made up of basalt rocks.
So if you are standing in Maharashtra, you are likely standing on cooled, rapid-hardened lava from millions of years ago.
Exactly. Extrusive fire rocks. That whole region is just layer upon layer of ancient volcanic flood basalts. It's one of the largest volcanic provinces in the world.
Then we have the opposite, intrusive rocks. Intrusive like inside.
Yes. Sometimes the molten magma cools down deep inside the Earth's crust. It never makes it to the surface. It gets stuck in a chamber, a magma chamber, miles below the ground.
And because it is inside, it's insulated by all the rock around it.
It acts like a perfect thermos flask. It keeps the heat in, so it cools down slowly, very, very slowly, sometimes over thousands or even millions of years.
Wow. Millions of years to cool down.
And because it cools so slowly, the mineral crystals have plenty of time to form and grow. They get big. So intrusive rocks form large grains.
The example here is granite.
Granite, the classic example. And the text gives a very relatable everyday example, grinding stones.
Right. The ones used for spices.
If you have ever seen those heavy stone mortars and pestles used to prepare paste or powder of spices and grains, that is usually granite. And if you look closely at a piece of granite, like on a kitchen counter,
You can see the different colors.
you can see them. The black specks, the pink specks, the white or gray specks, those are the individual mineral crystals. Mica, feldspar, quartz. You can see them because they are big. And they are big because they cooled slowly deep inside the earth.
That is the visual proof of intrusive formation. I will never look at a kitchen counter the same way again. So igneous is the parent rock, but the earth is dynamic. Rocks don't just stay rocks. They get beaten up by the elements.
That brings us to the second type, sedimentary rocks. The Latin word is sedimentum, which means to settle down.
But before they can settle, they have to be broken apart. The text describes the process beautifully. Rocks roll down, crack, and hit each other. They are broken down into small fragments.
This is weathering and erosion. Nature is constantly relentlessly attacking rocks with wind, water, ice, and even plants.
These small fragments are called sediments: sand, silt, clay.
Then nature's transport agents take over. Wind and water carry these loose sediments away. A river carries sand to the sea. The wind carries dust across continents.
And eventually they stop moving. They get deposited in a lake or on the ocean floor.
They settle. And over immense periods of time, layer upon layer of these loose sediments piles up. The weight of the overlying layers compresses the sediments below.
And the text says they are compressed and hardened to form layers.
Right, the water is squeezed out, and minerals dissolved in the water act like a glue, a cement, that binds the particles together. The scientific term for this whole process is lithification.
So stratification, the layers, is the key feature, right? If you see layers in a rock face, you're probably looking at sedimentary rock.
Exactly. And the text notes a very unique feature of sedimentary rocks. Something you don't find in igneous rocks for a very obvious reason.
Fossils. The remains of the dead plants and animals trapped in the layers of rocks.
Think about the logic there. If a dinosaur dies on a lava flow, an igneous environment, what happens to its body?
It's incinerated. It just burns to ash. No fossil.
Right. And if a dinosaur bone is in a rock that gets crushed and cooked by massive pressure, a metamorphic environment, it is destroyed or distorted beyond recognition.
But in a sedimentary environment.
The bone or the shell gets gently covered by sand or mud, layer by layer. It's protected from the elements it's preserved on. That's why these rocks are the history books of geology and biology. They're the only ones that keep a reliable record of past life.
That makes perfect sense. The example given is sandstone, which is, as the name suggests, made from grains of sand.
Simple enough. You take sand, you bury it, you squeeze it for 1 million years, and you get sandstone.
And for our monument connection, we have to link it.
The Red Fort in Delhi.
Right.
The Red Fort is made of red sandstone. So when you look at the walls of the Red Fort, you were essentially looking at ancient riverbeds or sand dunes that were compressed and cemented over eons. You're looking at time turned to stone.
Okay, so we have fire rocks, igneous, and settled rocks, sedimentary. But there is a third act in this play, the transformers, metamorphic rocks.
I like that, the transformers. The Greek word metamorphos literally means change of form.
And how does this happen? The text says it happens under great heat and pressure.
That is the recipe. You take any existing rock, an igneous rock like granite, or a sedimentary rock like limestone, and you subject it to extreme conditions. But, and this is a crucial distinction, you don't melt it.
Because if you melted it completely, it would just become magma again.
Exactly. Then you're back at the beginning of the cycle, ready to form a new igneous rock. Metamorphism happens in the solid state. The heat and pressure are intense enough to cause the minerals inside the rock to change, to recrystallize, to realign themselves.
So it's like baking.
It's a perfect analogy. Think of it like baking bread or cookies. You take dough, which has its own properties. You don't melt the flour into a liquid. You apply heat, and the chemical structure changes. It becomes something new, something harder and more organized. You cook the rock and squeeze it until it changes its chemical and physical structure.
The examples in the book are really helpful here. Clay changes into slate.
Right. Clay, which is a soft sedimentary rock, gets compressed and heated. The tiny clay minerals align themselves into sheets, and it becomes slate, which is a hard, flat, metamorphic rock.
And the other one, limestone changes into marble.
Limestone is a sedimentary rock, often made from the shells of tiny sea creatures. It's mostly calcium carbonate. You cook that limestone under intense heat and pressure, and it recrystallizes into a much denser, harder, interlocking structure called marble. The original shells are destroyed, but the chemistry is rearranged into beautiful marble.
And the monument example for this one is a big one.
The biggest, the Taj Mahal, made of white marble.
So structurally, the Red Fort is sedimentary, sandstone, and the Taj Mahal is metamorphic, marble. That's a great way to remember the difference in texture and hardness, too. Sandstone is grainy, marble is crystalline and smooth.
And much harder. Marble has been through the metamorphosis, through that trial by fire and pressure. It's a survivor.
This leads us perfectly into the rock cycle, the whole system. The text says, "You will be surprised to know that one type of rock changes to another type under certain conditions in a cyclic manner."
It destroys the idea of permanence in geology. We look at a mountain and think, that's solid, that's forever. But it's not. Geologically speaking, it's just a phase.
This is a temporary form.
Exactly. The Earth is the ultimate recycling plant. It creates no waste. It just repurposes matter over millions and millions of years.
Let's walk through the pathway described in the text so we have the cycle clear in our heads. Step 1. Molten magma cools and solidifies.
And that gives us igneous rock, the parent, the start of the process on the surface.
Step 2. Igneous rocks are broken down by weathering into small particles, which are then transported and deposited.
And that gives us sedimentary rock, the accumulation of the broken pieces.
Step 3. When igneous and sedimentary rocks get buried deep in the earth, they are subjected to heat and pressure.
And that gives us metamorphic rock, the transformation, the cooking and squeezing.
And the final step to complete the loop, step 4. The metamorphic rocks, which are already hot and under intense pressure, if they get subjected to even more heat and pressure.
They finally give up, they reach their melting point, they melt down, they become molten magma again. And the cycle is ready to start all over.
It is a continuous loop.
It is. It also means an igneous rock can be weathered into sediment, or it can be directly metamorphosed. A sedimentary rock can be weathered again, or it can be metamorphosed, or it can be melted. All paths are possible.
It implies that the floor we stand on is constantly shifting and changing. The granite in your kitchen counter was once magma, and before that, it might have been a sandstone that was subducted into the mantle, and before that, maybe a basalt on an ancient ocean floor.
It's a millions of years long process of planetary recycling. It's really profound when you think about it.
Before we get to the heavy-hitting UPSC questions, which I'm really excited about, let's briefly touch on the last section of the chapter, minerals.
Right. The rocks are made of minerals. The book gives a very precise definition: naturally occurring substances which have certain physical properties and definite chemical composition.
The key is definite chemical composition. A rock is a mixture, like a fruitcake, but a mineral is a pure ingredient, like shitter. Quartz is always SiO2.
That's a great analogy. The text highlights their importance to humankind. It pivots from pure geology to economic geography here. It lists fuels as a major use.
Coal, natural gas, petroleum.
These are mineral resources, technically organic in origin, but found in sedimentary layers, and they power our entire civilization.
And then industries.
Iron, aluminium, gold, uranium, these are the building blocks of everything we make, from cars to computers to buildings.
It also mentions medicine and fertilizers.
It really shows that geography isn't just about memorizing the names of mountains. It's about understanding the resources that we depend on to build our world. Civilization is built on digging these things up out of the crust.
There's also a fun little activity in the text where they show common objects and ask what minerals they are made of. A car-high, ornaments, a bell, a hammer, a lamp.
It's a great way to ground the abstract geology in daily life. A car-high is usually iron, ornaments, obviously gold or silver. The bell is interesting. Bells are usually made of bronze or brass, which are alloys, not pure minerals.
But the base minerals would be?
The primary minerals would be copper and tin for bronze, or copper and zinc for brass. A hammer is iron. It just reminds us that we are literally cooking in and wearing the Earth's crust.
We are completely dependent on the lithosphere for our material existence.
100%.
Okay, brace yourselves, listeners. This is the payload. This is why you are listening to Simplified UPSC by PPP. We have covered the 7th grade basics. We have our vocabulary straight. Now, we're going to see why this matters for the UPSC Civil Services Mains.
Let's do it.
We have pulled questions from 2014, 2016, and the 2025 General Studies Paper 1.
This is where we bridge the gap. We take the vocabulary we just learned, crust, mantle, magma, sedimentary, Sial, Sima, and we apply it to solve these complex questions.
Let's start with the most recent one, 2025 General Studies Paper 1, Question 16. The question is, discuss how the changes in shape and sizes of continents and ocean basins of the planet take place due to tectonic movements of the crustal masses. It is a 15 marker, so about 250 words.
Okay, let's unpack this. The key words are changes in shape and sizes of continents and ocean basins. And the mechanism is tectonic movements of the crustal masses.
Where's the direct link to Chapter 2? This sounds more advanced.
It sounds advanced, but the entire answer is built on the foundation of Chapter 2. To answer this, you need to understand the relationship between the layers we just discussed.
Okay, break it down for me.
Chapter 2 introduces the crust and the mantle. Critically, it distinguishes between continental crust, Sial, and oceanic crust, Sima. The question uses the phrase crustal masses, that is your Sial and Sima. The question asks about movements. Why do they move? The book gives you the answer. Chapter 3, which is the immediate sequel to this, explicitly states the lithosphere is broken into a number of plates known as the lithospheric plates. And why do they move? Because of the movement of the molten magma inside the Earth.
So without understanding the molten magma in the mantle from Chapter 2 and the plates of the crust, you cannot explain why continents change shape.
You cannot build the argument. Your answer must start with the structure from Chapter 2. You explain that the lithosphere isn't a solid, unbroken shell. It's fragmented into plates. You explain that the intense heat from the core, the knife we talked about, drives convection currents in the mantle.
Like boiling water in a pot.
Exactly. The text even compares it to a paper pellet boiling in water. That's the engine. This convection in the mantle pushes and pulls the crustal plates of Sial and Sima that are floating on top.
And that's what changes the shape of the continents.
That's what does it. This movement causes the continents to drift, to split apart, to form new ocean basins, and to collide to form supercontinents. Your answer is a direct application of the crust-mantle relationship defined in Chapter 2. You go from a simple definition to a complex dynamic process.
That is a direct line from paper pellet in boiling water in an NCERT book to explaining the tectonic evolution of ocean basins in a mains answer.
It is the same concept, just with more sophisticated language. You build your answer on the foundation of Sial, Sima, and magma.
Let's look at another one. This is from 2014 General Studies Paper 1, Question 17. The question, why are the world's fold mountain systems located along the margins of continents? bring out the association between the global distribution of fold mountains and the earthquakes and volcanoes.
This is a classic physical geography question. And again, the answer is sitting right there in the concepts from Chapter 2. Look at that key phrase, margins of continents.
That brings us back to the Sial and Sima discussion, doesn't it? The edges where they meet.
It does. The margin is the boundary. It's where the continental crust, Sial, meets the oceanic crust, Sima, or sometimes where two continental plates meet, like with the Himalayas.
Okay.
We know from Chapter 2 that these crust types have different thicknesses and densities. When these two plates, driven by the mantle's convection, collide at the margins, what happens?
One has to give way.
Right. And remember how we talked about sedimentary rocks forming layers in the oceans between the continents? Imagine pushing a rug or a tablecloth from both sides. What happens to the rug?
It crumples up. It folds.
Exactly,
Cool.
it folds. That gives you fold mountains. The thick layers of sedimentary rocks that were deposited in the shallow seas between the continents get squeezed, compressed, and buckled upwards to form mountain ranges like the Andes or the Himalayas.
Wow. Okay, that's the mountain part. But the
Yeah.
question also asks about the association with earthquakes and volcanoes.
Well, it's all part of the same process because this is a zone of immense stress where the crust is breaking and colliding. You get earthquakes. That's the release of that stress.
And the volcanoes.
Because the crust is being fractured, and in many cases one plate is being forced down or subducted into the hot mantle, it starts to melt. This creates new magma.
And that magma from the mantle, which we know is waiting right below, finds a path to escape through the cracks.
And that gives you volcanoes. So you get this perfect chain reaction, mantle convection, plate movement, collision at the margins, folding mountains, plus breaking earthquakes, plus melting volcanoes.
So the magma defined in Chapter 2 is the fuel for the volcanoes in the question. And the sedimentary rock layers are the material being folded into mountains.
Yes. If you don't know that the crust is thin and fragmented or that magma exists beneath it, you can't explain why volcanoes and fold mountains appear together in long chains at the edges of continents. The NCERT provides the fundamental structural logic.
It makes the complex question seem almost simple when you break it down like that. Let's do one more. This is fascinating. 2025 General Studies Paper 1, Question 19. This one seems different. Achieving sustainable growth with emphasis on environmental protection could come into conflict with poor people's needs in a country like India.
Okay, this seems like an economy or an ethics question at first glance. It's about policy, about development, but look closer at the root cause of the conflict.
Okay, the conflict is environmental protection versus poor people's needs.
What are the needs of a developing economy? What lifts people out of poverty? Often, it is industrialization, it's jobs, it is energy, it is infrastructure.
And where does that come from?
It comes from the ground. It comes directly from Chapter 2, the section on minerals.
Of course.
The text says, minerals are very important to humankind. Some are used as fuels. For example, coal, natural gas, and petroleum. They're also used in industries, iron, aluminium.
So developing nations need these minerals to build their economy. That addresses the poor people's needs part of the question.
Yes, you need to build steel plants, you need coal for electricity, you need bauxite for aluminum. This creates jobs and drives growth.
But the extraction, the mining and drilling,
The extraction is the point of conflict. It often involves destroying the lithosphere, the very crust we just studied. It impacts the biosphere from Chapter 1. Open pit mining for coal or iron ore removes forests and displaces communities. Drilling for oil risks spills that destroy marine ecosystems.
so the conflict arises directly from the extraction of the resources mentioned in Chapter 2.
Precisely. To answer this question well, you can ground your argument in this geographical reality. You can cite specific examples. You can say, as fundamental geography teaches us, our industries and energy sectors are dependent on minerals like iron and coal found within the Earth's crust.
And then you can build the ethical argument on top of that.
You can argue that while we need the minerals from Chapter 2 for economic growth, the process of getting them can cause irreversible harm to the environment. Chapter 1. It grounds your philosophical argument in material reality. We are fighting over the use and misuse of the lithosphere.
It is incredible how these simple chapters provide the raw material for such complex interdisciplinary arguments.
That is why we call it the deep dive.
Huh.
You aren't just memorizing core Nife. You are learning core Earth's magnetic field, mantle, the driver of tectonics, minerals, the foundation of economic conflict. It turns simple facts into powerful analytical tools.
Let's just do a quick recap of what we have unpacked today. We covered a lot of ground, literally.
We started with the structure of the Earth, the onion.
We had the crust, the thin skin, Sial for the continents and Sima for the oceans. Only 1% of the volume, but it's where we live.
Then the mantle, the thick, fleshy part, 84% of the volume. The source of magma and the engine that drives all the movement on the surface.
And finally, the core, the hot, dense center, Nife, nickel, and iron. 15% of the volume and the source of our protective magnetic field.
Then we cover the 3 rock types.
Igneous, the fire rocks, form from cooled magma. Fast cooling on the outside means small crystals like basalt. Slow cooling on the inside means big crystals like granite.
Sedimentary, the settled rocks, made from compressed sediments. These are the only rocks with fossils, our history books, like sandstone.
And metamorphic, the changed, transformed rocks, cooked by heat and pressure into something harder and denser, like marble.
We then trace the rock cycle, seeing how magma becomes rock, breaks down, settles, gets cooked, and eventually melts back down into magma. It's a dynamic, constantly recycling Earth.
And to top it all off, we linked it all to the UPSC Mains, showing how tectonics, fold mountains, and resource conflicts all stem from these basic fundamental definitions from a 7th grade textbook.
It is a comprehensive picture from the center of the Earth to the exam hall.
Before we go, I want to leave you with a thought, a provocative thought to mull over. We talked about how we have only drilled 6 kilometers into a 6,371-kilometer radius planet. That means 99.9% of our home is theoretically unknown to us directly. We rely on those echoes, the seismic waves, to see inside.
It's all indirect.
Right. The text says the core is nickel and iron, but that is our best scientific model right now. What if our understanding of the core changes in the next decade? We're getting better seismographs, better computer models. There are already new theories about these massive blobs and the lower mantle anomalous structures the size of continents that we can't fully explain. What are they? Are they remnants of an ancient planet that collided with Earth? We don't know. So my question is, if our understanding of the engine room changes, how would that change our understanding of everything else?
You mean like the magnetic field?
Exactly. How would it change our understanding of the magnetic field that protects us from solar radiation? Or our understanding of how continents move, the very speed at which they move? What if the engine is more complex than we thought? We are, quite literally, standing on a mystery.
That is a humbling thought. We think we know the ground beneath our feet, but it's the biggest unexplored territory we have. We are very small creatures on a very large, very complex, and still very mysterious sphere.
On that note, we are going to wrap up this deep dive. Once again, a huge request from us. Please subscribe to Simplified UPSC by PPP on YouTube. It is the best and easiest way to support this series and ensure we can keep cracking open these textbooks for you.
And if you are in a position to, and only if, please check out the Patreon. Every bit of support helps the team research, script, and produce these deep dives.
Don't forget about the private Telegram library. It's a treasure trove. If you want premium notes that detail everything we just said, plus extra PYQs and model answers for those mains questions we discussed, DM us on the public Telegram channel to join.
And please like, share, and comment. We love hearing from you. Tell us what topic you want us to crack open next.
Until next time, keep digging deep.